Next, we have Kumar Saurav from TIFR. He will talk about minimizing the sum of age of information and transmission cost under stochastic arrival model. Over to you.
Thank you, Pranshu. Thank you for reading out this long title. But basically, we will consider a trade-off between age of information and transmission cost. I think this will be a nice one. So this is a joint work with my advisor, Rahul Vaze, and this work that I will present today will appear in Proceedings of IEEE Infocom 2021. Okay, so so, so consider the following setup. So for example, let's say you are a head of the Microsoft developer team, and software updates are developed by your programmers uh, with inter-arrival time x1, x2, x3, and so on, where these xi's are IID according to some known distribution D, and there are users who need these updates. However, as a head, you need to decide when to transmit these updates to the user, because every transmission costs C units. So here, C units, this encapsulates so every time there is update, so the device needs to be restarted, etc. So and there is bandwidth cost in transmission, etc. So this so every time the software is update is transmitted, there is some cost. So as a head, you need to decide when to transmit. You may want to transmit as much updates as possible once, instead of transmitting it in different one after the other in multiple tranches. Um, but you also want that the device should have latest updates available with it, so that for various reasons such as security and performance. Um, at any time, you want that the age of the latest update available at the device is low. Age here in the sense means like how old the latest update available with the device is. To understand this, so we will plot the age of information. So basically here information, I means the latest age of the latest update that is already available with the device, user device. So to start with, the user bought the device that had like the latest updates installed. So the age of information is 0. As time progresses, this updates becomes old. Let's say at time t is equals to 2, some new updates are generated at the server, but it is not transmitted to the user. At time t is equals to 3, update is transmitted, and so the age of information drops. So it drops to 1 because at time t is equals to 3, the update that the user received is already 1 time units old. Uh, Again, as time progresses, this age of information increases. Let's say again at time t is equals to 5, an update arrived at the server, and this time it was transmitted immediately. So the age of information is now 0 because now the user has the latest update at time t is equals to 5. Similarly, say at time t is equals to 6, another update arrived. But as you can see, the age of information is already not very large. So the server may not transmit it. So it doesn't transmit it. And again, another update arrives at time t is equals to 7. So at now this time the server transmits it again. So age drops to 0. So as we can see, the server need not transmit all the updates, and in this way it can actually save some transmission cost while also have low age of information. Formally, this age of information is defined as at any time t, the age of information is the current time t minus the arrival time of the latest packet or update that has been seen by the that has been received by the user until time t. Um, so here arrival time means when it arrived at the server, server that is here in the between. So it is the arrival time at the server. Um, so clearly there is trade-off between age of information and transmission cost, because at every time if you want to have the age of information to be low, you need to have a packet that arrived very recently. And it is available at the user. So there is a trade-off. And particularly we don't have a constraint as such. So we can't say that, again, constraint needs to be formulated very precisely. So we formulate this problem as follows. So the objective, we can have the objective to minimize the linear sum of average transmission cost and average age of information cost. And we just want to minimize this linear sum. So this is a weighted linear sum. For simplicity, I have just subsumed this this weight inside this cost per transmission C. So that will take care of it. So this is, so the objective is to minimize the weighted linear sum of average transmission cost and average age of information cost, where this at any time t, the average transmission cost is equals to the cost per transmission C time number of transmissions until time t divided by t, and the average age of information cost is the area under the age of information plot until time t divided by the time t. And we have the objective is to minimize this weighted linear sum as time t tends to infinity. So similar, so basically this age of information related problems are studied for two models. One is stochastic packet arrival, where these updates actually arrive stochastic, and one is the generate at will model. So for example, when you have, for example, when the user can actually, when the updates can be generated whenever the server wants. So it can generate the update and it can transmit. Um, but mostly this trade-off between age of information and transmission cost has been considered for generate at will model, and stochastic packet arrival model appears to be, I mean, slightly more involved. Uh, in energy harvesting setup, however, there has been like such trade-offs have been considered, but there the randomness is not in terms of the packet generation, but in terms of energy arrival. So the transmission cost is in terms of energy consumed, and the energy arrives stochastically, and anytime you can transmit if you have enough energy. So that is the constraint there. So but this, as already said, so this stochastic packet arrival setup is challenging and very practical in a lot of sense. So so we consider this particular model in this work. So the merits of this work is like if inter-arrival time of packets, we said the inter-arrival time of packets follow like some known distribution D. So if that distribution D is exponential, we show that a threshold-based policy is optimal. So that is, if at any time, if age of information is greater than a threshold A star, then just transmit the arriving packet. So as soon as a packet arrives, just transmit it. And we also find this optimal threshold A star. And for any general distribution, any light tail, so any general distribution, so we propose a stationary randomized policy, and for that we show that its cumulative ratio is upper bounded in terms of inter-arrival time, and but it is good in a lot of sense, because for several common distributions such as exponential, uniform, this competitive ratio is at most equal to 2. So for exponential distribution, so this presentation will be mostly like in two parts. So first is exponential distribution, and second is for general distribution. So when interval time follows exponential distribution, we follow a 3-step approach. So first we identify some structural properties of an optimal causal policy. And then we use that policy to derive a lower bound on the total average cost. That is basically the objective function. So we find a lower bound on that, that any optimal causal policy would incur. And we propose a threshold policy that achieves the lower bound that we derive in step 2. So here's this optimal causal policy. I mean, from causal policy, I mean any policy that has all the information in the past, but nothing about the future. So in step 1, this structural property, so basically we could show that there exists an optimal causal policy that either transmits a packet immediately after arrival or never transmits it. That is, there is no buffer. So whenever there is an update arrives, so at that instant, the server transmits all the update at once, and otherwise it never transmits it. So we can see it from this plot. So packet arrived at 1, 3, and 4. It at 1 at time 1 and time 4, but didn't never in between. So now, so how we got this property? So basically consider this interval between two successive packet arrival times. It can be like one can it can be shown when the interarrival time is exponentially distributed at any time t in between this interval 1 and 3. The information available at the server about the next packet arrival is same as it had when the previous packet arrived at time t is equals to 1. Um, so if it transmits at any time after that, after the previously arrived packet, before the arrival of next packet, the expected cost incurred by it is actually large. So it could have better transmitted it at the arrival time of the previous packet. This what it helps us is, in the set of all causal policies, we were looking for the optimal causal policy. This property actually narrows down the search space to a small set of policies, no buffer policy, that either transmits a packet immediately after arrival or never transmits it. Now for this,
Kumar, you can also have some distribution where, given that it's not arrived, that's telling you something about when it will arrive next, right? Some kind of
yeah.
increasing or decreasing.
Yeah. So basically, this
get
exponential
same
distribution has
yeah.
Yeah.
You can use a
so we will consider
okay.
Yeah. So actually, so for general distribution, we will see that when so in general distribution, this property does not hold. So we will consider it in part 2 this presentation. Now for this, when we are looking at only no buffer policies, then this entire age of information plot can be broken down into cycles, where a cycle denotes the interval between where a cycle is the interval between two successive time instants when the age of information is 0, and we call this length of this interval as t. And in each cycle, the age of information cost is basically t square by 2. The area under the curve in this cycle, that is t square by 2. And exactly one transmission happens in each cycle at the end of the cycle. The transmission cost in a cycle is c. So the total cost in a cycle is t square by 2 plus c. And the total average cost, so we basically sum this over all the cycles. So we sum the cost for each cycle, for all cycles, and divide it by total time. That is again the sum of the cycle lengths. And using renewal reward theorem, we can write it in terms of expectation, mean of cycle length square and mean of cycle length. And basically, we expand this mean of t square in terms of variance of t and the square of mean t, and we get the following expression for total average cost. So basically, now the objective is to find the policy that minimizes this total average cost that we have here. So for any no buffer policy, this is the expression for the total average cost. Now in step 2, we find a lower bound on this. So note here that we can only control the cycle length t, but the total average cost is in terms of the mean of cycle length t and variance of cycle length t. So for the lower bound, what we can do is we can basically minimize this total average cost with respect to variance of t and mean of t independently. So in general, they will be related, but because we want a lower bound, we can minimize them independently. And we can also see that this total average cost for any mean t, for any fixed mean expectation of t, this total average cost decreases linearly with decrease in variance of t. And for any fixed variance of t, this total average cost is convex in mean of t. So what we can do is, so we can first minimize it with respect to variance of cycle length t, and then for fixed variance of t, we can minimize it with respect to mean cycle length of t. Then for exponential distribution, we can again establish another fact that this variance of cycle length t is at least equal to the variance of interarrival time of packets, because we are only transmitting a packet when it arrives and not otherwise. I mean, we only transmit the packet when it arrives or never transmit it. So if we don't transmit a packet, we will certainly have to wait for the next packet. And because of memoryless property, at any time we have like similar, we will have to wait for X amount of times. So where X is again exponentially distributed. So that is why from where there we get this fact. So for minimizing with respect to variance of t, we can substitute this variance of t with variance of inter-arrival time of packets x, and for this fixed variance, we can minimize with respect to mean cycle length t, and we get that the total average cost is at least as much as shown here. So at least as much as square root of variance of inter-arrival time of packet x plus 2c, where c is cost per transmission. 3 policy, which is basically a threshold based policy. So if age of information is greater than a star, then transmit the arriving packet immediately, otherwise just discard the packet. So to understand this, let's see the plot. So when the age of information is less than a star, just don't do it. Any packet that arrives, just throw it away. And once the age of information is equals to a star, if any packet arrives, just transmit it immediately. Now, so again, we have a cycle here. So from time t is equals to 0 to time t is equals to 4. So this cycle actually can be partitioned into two intervals. One, when the age of information is less than a star, and second, when the age of information is greater than a star. Now, because of memoryless property, standing at time when the age of information is exactly equals to a star, the next packet arrives after time x. I mean, this time interval has distribution like is exponentially distributed. So basically, this cycle length t can be written as a star plus x, where x is the inter-arrival time of packets. And so taking mean on both sides, so we get mean cycle length is equals to as shown. And similarly, variance of cycle length is variance, because this a is constant. And we already have expression for the total average cost. So the substituting this variance of cycle length t and variance of like mean cycle length t, we get this total average cost for this proposed policy, which is exactly equal to the lower bound that we derived in step 2. So this shows that this threshold-based policy is optimal, and we do have this threshold. We got this threshold. Now, for general distribution, so I don't assume anything about this distribution, but for the result to be nice, I would assume that this is a light-tailed distribution. Now, so because an optimal policy need not transmit. So as Sandeep said, so you can have distribution when after waiting for some time, you get better information about when the next packet will arrive. For example, if you know that when a packet arrives, the next packet arrive in the next just immediately after that, with very high probability, and with a very low probability arrives at a very large time. I mean. Then you might transmit then you might wait for some time for the next packet. But this is the property that we already derived. So a no buffer policy need not be optimal. So an optimal policy need not I mean a policy that transmits packet immediately or may not. So we propose a stationary random policy. For this policy, we derive a guarantee that guarantee in terms of competitive ratio, and so that it is even this the total like average cost for this policy is not very far from the optimal policy. So just to recall, so this competitive ratio of any causal policy pi is the ratio of the expected total average cost for the policy pi divided by the expected total average cost for the optimal offline policy. So an optimal offline policy basically has all the information about packet arrival times in past as well as future. So no causal policy can do better than this optimal offline policy. Yeah, so this gives a guarantee for the performance. Now, so consider this randomized policy. So transmit the arriving packet immediately. So any packet arrives, just transmit it with probability P star and reject it with probability 1 minus P star, where P star is given as follows. So note that this randomized policy is a no buffer policy, although no buffer policy need not be optimal, but consider this policy which is a no buffer policy. And this P star is basically if the mean interarrival time of packets is large. So if a packet has arrived at now, and if the expected time after which the next packet will arrive is very large, so you may want to transmit the packet like so is high. So you transmit packet with high probability, and if the is large, you may want to transmit it less. So P star is like inversely proportional to this, has relation with cost per transmission C. And for this, the competitive ratio is at most given as follows. So so this depends on the variance of interarrival time divided by mean interarrival time of packets square. But interestingly, common distributions, this is actually less than equals to 2. So in that sense, this is nice. For heavy tail distributions where variance of x is very large compared to its mean, this competitive ratio is like unbounded. How do we how do we get this competitive ratio bound? Basically, basically. Proposed policy is a no buffer policy. So it transmits a packet immediately after it arrives or never transmits it. So for policy, we already have an expression for total average cost, right? Which is in terms of the cycle length T, where again, just to recall, the cycle length is the length of the time interval between two successive time instants when the age of information is 0. And and for this policy, we can derive this variance of cycle length T and mean cycle length T policy known. And so we can compute this total average cost. And for offline, optimal offline policy, this is also policy. Offline policy, so optimal causal policy need not be no policy, but offline policy must be a no buffer policy because it knows the arrival time of all the packets. So for example, in the figure here on the left, so if transmitting packet at time t is equals to 1, if a policy transmits it at time t is equals to 2, it incurs a greater age of information cost. For same equal number of for equal cost, it incurs more cost. So basically, so this policy can't be optimal because I can reduce my information cost just by transmitting the packet at time t equals to 1 itself. Now, so for this optimal policy, we don't know the variance of cycle and etc. So what we do is but we have the same expression for total average cost given on the left. What we do is for the lower bound, we assume variance of length t to be 0. So we can also this lower bound for any policy. And for this, when variance is 0, we minimize the cost with respect to mean cycle length t. So we get the lower cost for optimal and the ratio of the total average cost for the proposed policy and lower bound on the optimal offline total average cost of offline policy, we get an upper bound on the competitive ratio. So this was for general distribution case. So any doubt here?
So Kumar,
so,
let me ask you a question. So at any time, you know the age of when you last sent an update, and you know the last time the distribution of the update, right? So you know the how much time has already happened since the last update came to you. So you know that, you know the distribution of the inter-arrival time of updates. You know the last time this update was actually implemented. So it should be a function of these two things, right? What you do, function of how, when the last update came and when the last update was implemented or something. Just these two pieces of information, right?
Yeah. So for exponential distributed case, we
It
do
becomes
use,
one.
so this age
Yeah.
of, yeah. So for age of function, that we are basically packet arrive. So we use that fact.
Yeah, so that's right.
Distribution case,
So so for exponential, it becomes a one parameter issue. So that's why you have a threshold policy. But more generally, you're looking at the space of two pieces of information, and you have to partition the space as to where you, I guess, transmit and where you don't transmit, right? Is that fair? Is that the optimization problem?
So,
yeah. So,
maybe his connection is poor. So maybe let me answer.
Go ahead. Yeah, you can decide.
So yeah, so what you're saying is correct. It's just that one can possibly show that the optimal policies are the threshold kind, which depends on both the parameters. Instead, what we're doing here is that we're proposing a particular policy and trying to show that it's not too far from optimal, which only depends on one parameter.
Right. So now, in some sense, you can say that your policy will work even if you did not know the distribution of patches, the inter updates coming in.
So it only depends on the expected value of the inter-arrival time.
Okay.
So as long as you know the first moment, you're fine.
Okay. It's probably good to have all these three pieces, I guess, because the intermediate piece as well.
That's true, but it's just that it's a complicated business.
Sure.
One can possibly show that the policy of the threshold type, but finding thresholds is very hard.
Okay.
So any more questions? So in this talk, we considered this trade-off between age of information and transmission cost, and we formulated the problem as a minimization problem, like that seeks to minimize the sum of average age of information and average transmission cost under stochastic packet arrival model. And we considered two cases. First one was like exponential distributed arrival time, showed that policy is optimal, and we also this optimal threshold. And for general distributed inter-arrival time, we proposed a stationary randomized policy, and for this we found a competitive ratio which for several conditions is less than 2. Thank you.
Thank you, Saurabh. We have time for a quick question. Are there any questions? If there are no more questions, then I would like to thank Saurabh again. Over to Jay Kumar.